This is the lecture regarding the logistic regression. As we discussed the regression analysis earlier before this lecture, that our dependent variable y is a scaled variable, as well as independent variable are also the scaled variable. But in logistic regression, your dependent variable should be a dichotomous variable. So your dependent variable is a binary variable, which has only the two possible values, either yes or no, or 1 or 0. If you have this type of variable, we can predict the value of this type of variable by using the regression, logistic regression. So your scale dependent variable can be predicted by the regular regression, and your dichotomous dependent variable can be predicted by using logistic regression. There is a special kind of model. It has the dependent variable has only the two values which are represented here on the graph. The value this is and the value this is. This is the probability 0, probability of having the outcome 0, and this is the probability of having the outcome 1. In between the 0 and 1, there is nothing. Suppose this is the age of the customer and it is the energy level of the participants. So we can see that, or we can another way we can call it as the response variable y is a variable which we can predict. For example, the loan will be approved or not approved. If the customer having the higher age, older age, so the probability of approval of the loan is 0. And if the customer having a smaller age, like a younger age, then there is a probability of high probability of having to approve the loan, right? So it has only the two values. The age is very high, then the probability is almost 0. And if the age is very small, young people above 18, then the probability of giving the loan is 1. So only these are the two possible values, right? In the other ways, we can have the situation, but in a very simple situation, we can predict the dependent variable by 0 or 1. This is called dichotomous dependent variable. Ordinary regression, if we predict the probability by using the ordinary regression, which is referred to as OLS, ordinary least square. Ordinary least square does not model the relationship well. If we predict the probability by using the ordinary least square, then the probability model will be like the straight line, like it. The value is around 1, very high value, or the value of y is about 0, very low value, but it can be negative. In this case, you can observe that the value can be the negative value. These are the values of the probability which are negative, and these are the values of the probability which are above 1. So we have to transform the OLS by a function which will give us only the value in between 0 and 1. That dependent variable is called, that model is called the logistic regression. The logistic regression is not a new model for you. It is a transformation of ordinary least square. Your ordinary least square will provide you this straight line, but we have to transform the ordinary least square in a function like it. This is called sigmoid function. You can see it in a reverse order, but generally this function is like a cumulative probability. This is called S function or a sigmoid function. So logistic regression is basically predicting a sigmoid function. While the ordinary least square is providing us what? This is the straight line which ordinary least square will gives us. So we have to transform the ordinary least square into a sigmoid function. The probability of having the sigmoid function is referred to as logistic regression. So this is the summary, this is the introduction of the logistic regression. The properties we need for the logistic model, the model should be bounded by 0 and 1. The model should estimate the value of the dependent variable in terms of the probability. What the model will give us, this will not giving us a scaled value of dependent variable. This will give us a probability of the dependent variable. An owner or the renter, pass or a fail, default or not, perish or survive, etc. These are the different situations or scenarios in which we have to apply the logistic regression. For a logistic regression, your DV should be dichotomous, but your IVs may be scaled or may be dichotomous. There are the several situations of the model. If your DV and IV both are scaled, we can apply the ordinary logistic regression. We want to know the probability P that a particular case falls into the 0 or the 1 category. We want to derive a model which gives a good estimate of 0 and 1. Or put another way, that the particular case is likely to be 0 or the 1. In simple, we can say that the logistic regression, we are interested in to predict the probability, and the range of probability is 0 and 1, any value. But my DV in the logistic regression is only have two values. But the logistic function will not give you only the two values. Logistic regression will provide you the all probabilities, and these probabilities will be in the range of 0 up to 1. So we will predict the probability by the logistic function, and the probabilities by the logistic function will be 0, 1 in the form of interval. In the form of interval means these values in between the 0 and 1 will also be included in the model. Then finally, after getting the value of the dv in the form of probability, we will convert the situation into the two values which are 0 and 1 only. This function is referred to as logistic function. So your logistic function is a function which gives us the probabilities like it. E raised to the power. What is it? You can imagine this. This is the value of the variable y by the OLS. The very simple thing is what? So your predicted y cap. This is your y cap by ordinary least square. So you have to form a function e raised to the power y cap divided by 1 plus e raised to the power y cap. This is called logistic function. What is y cap? In ordinary least square, y cap is beta naught plus beta 1x. Or in simple, we can write down as b naught plus b1x. So this is your OLS, ordinary least square. And if you raise the predicted value of OLS e raised to the power y upon 1 plus e raised to the power y, then this line, this is a straight line. This straight line will be converted into a function which is referred to as sigmoid function. So this is a transformation only. We are transforming the y into this. And this is same as this one. Why this is same as this one? Because e raised to the power y, no, y means what? e raised to the power, the value of y is this, b naught plus b1x divided by 1 plus e raised to the power y cap means what? 1 plus e raised to the power b naught plus b1x. So this is the function which is referred to as logistic regression. The graph of the logistic function is a sigmoid function. It gives us the probability 0. You can see that the probability is 0. As we are decreasing the very independent variable v5 towards the left side, the probability is decreasing and decreasing towards 0 only. It's a asymptotic behavior it has towards 0. And it has asymptotic behavior towards the plus infinity. So as the variable v5 is increasing, the probability is becoming closer and closer to the 1. And in between the 0 and 1, we have the all values. Suppose at 2, the probability is this. At 1, the probability is this. So this is what? This is just the probability. Can you imagine the formula of this probability? Very simple. The formula, the predicted value of this probability is 1 e raised to the power y divided by 1 plus e raised to the power y. This is the formula. And what is y? And the y is the simple linear regression. So this is y. This is y or y cap. If we transform this y into the probability, then p is the sigmoid function. So that is a very simple transformation which we are going to apply over the ordinary linear regression. Now, one function is the logistic function. Now we have to transform this function into the y. So how can we convert this function into the y? We can convert this function into the y by taking odd. So in probability, the odd is what? Odd is the probability of occurring something divided by the non-occurring. Probability of non-occurrence is in denominator, P upon Q. In a binomial distribution, P is the probability of success, Q is the probability of failure. Odd is what? Odd is the probability of success divided by the probability of failure. This is called odd in probability. So if you are computing the odd, the logistic function can be written as ln odd is equal to ln p upon 1 minus p, taking the log both sides. When you take the log both sides, then this form of the function is called Logit function. The Logit function is this, in which we have the log of the odd. And odd is what? Odd is the probability of success divided by the probability of failure. This is called the odd of the function. Now, the value of y cap is actually the log odd. So what is it? On the right side, we have the y cap. Y cap is what? Is a simple linear regression. And on the left side, what we have? ln p upon q. This is called log odd. So log odd is the y cap, right? So we have to, now that we have the two functions. One is called logistic function, other is called logit function. So this function which is in the screen is a logit function, and the logistic function, it is in the form of the probability. If the function is in the form of log odd, it is called logit function. If the function is in the form of probability, this is called logistic function. These are the two different formats of writing the logistic regression. Sometimes we write down the equation in the form of probability. Whenever we have to predict the probability, it is in the form of p cap. Whenever we have to predict the log odd, the function will be in the form of logit function. Logistic function can also be written as, the actual function was what? The actual function was p cap is equal to e raised to the power y divided by 1 plus e raised to the power y. Y e raised to the power y divided by 1 plus e raised to the power. But if we transform the numerator to the denominator, how can we transform the numerator towards the denominator? Very simple part. If I take e raised to the power y in denominator, so I can write down this function as 1 upon 1 plus e raised to the power y into e raised to the power minus y. This e raised to the power plus y will be shifted in denominator by e raised to the power minus y. If I multiply this by first time this and second time this, because in the bracket we can multiply these two. So e raised to the power plus y, e raised to the power minus y becomes 1. This is 1. And e raised to the power minus y and 1 becomes e raised to the power minus y. So the value of y is what? The value of y is b naught plus b1x. This is your value of y cap. So if I put the simplified version will be what? 1 plus e raised to the power minus y. This is the final version of this. And if I put the value of y like it, so the function is this. So this is the another form of the logistic function. So now, right now, I have the three forms. One is called logit function. Second one is the logistic function. First form. This is the logistic function. Second form. Which form is simple? This one, which is written on the screen, is the simple form of logistic function. Now, example. Now we are considering one complete example of a data set in which we are implementing the logistic regression using R. And this data set having one dependent variable, which is CHD, stand for congenital heart disease, is a dichotomous variable. If the person have a CHD value 1 means congenital heart disease is 1. Otherwise, it is 0 means the person does not have the problem of congenital heart disease. And the second thing is the age variable, which is the person age or the patient age. So these are the two variables. My dependent variable is CHD. My independent variable is age. And we have to predict the CHD by age. If we apply by assuming this is y, this is x, ordinary regression equation, so the estimated value will be represented by b naught plus b1x. If we apply the simple model, then your y cap will be this. But we are not interested to build a simple model because in simple model, the y will be 0, the y will be 1, but the y may be negative, the y may be greater than 1. Because in simple linear regression, the line will be like it. Any value we have below 0, any value we may have above 0. So this is the difference between simple and the logistic regression. So we have to apply the logistic regression here, not the simple regression in R. So the function of R for implementing the logistic regression is GLM. If we have to apply the simple linear model, the function is LM. If we have to apply a logistic regression model, the function is GLM. So LM for the simple linear model and the GLM for generalized linear model. So you will apply the function GLM instead of LM to apply logistic regression. So how to apply the logistic regression? Just look at the data set, your variable age is a continuous variable, and another variable age is an age categorical variable. Binning is performed by the variable age. The age cat will be obtained. And the last column is the CHD, yes or no, 0 or 1. The probability is 0. The person is involved in the disease, yes. The person doesn't have this disease, no. There are the 9 rows only, very short data set it has. First step is to read the data file by the read.csv command, and I have used the function file.choose. What file.choose will do? File.choose will open a dialog box which allow me to select the folder, which allow me to select the file of CHD. The file name is chd.csv. This file we have to open by the read.csv command, and the new data frame is chd data. This is my data frame in which the entire data is stored. Very simple data we have. Summary CHD can give you the entire summary statistics of all variables. There are the 3 variables. One is a categorical variable age. Another is the continuous variable age. The age has the two versions age has, and the third one is the value of the CHD. So now we first have to convert the CHD variable into factor, because CHD variable was in character, and before using the logistic regression, your 0 and 1 or the categorical variable should be converted into the factor by as dot factor command. So the CHD variable of the data set is converted into the CHD, and the new CHD is also stored in the same variable. Means it is a replacement of the previous variable by a new variable. If you saw the structure of the new variable, so you can see that the categorical variable converted into the factor. What the attach function do? Attach function will allow us to remove the data frame name before the dollar sign. So that is a very simple way to remove the data frame name before the variable name if you attach the file by using this function. The next command is a command which gives you the output of the variable age and the CHD. This is a straight line according to the linear model, but we have to apply a generalized linear model. So instead of the linear model, we are applying a generalized linear model. So what was the function which I taught you to implement the DV first and the tilde sign, then your IVs. If you have only one IV, then write down it. This was the simple linear model. But if you want to apply a generalized linear model, so instead of LM, you have a GLM. Another change is what family is equal to binomial. This is the change which we have here in the variable, right? Now the summary of the model as usual, and the predicted value of the response. For the predicted value, you have to supply the model, and the next thing which is to be provided, the type response. Response is the yes or no variable which we are getting as a predicted value. So what is the PRED? PRED will give us predicted values by the model. And if we plot the line between the age and the predicted values, so age and the predicted values will give us a sigmoid function, because predicted values as the predicted probabilities. So if we are plotting the probabilities, then the graph will be like a sigmoid function. So this is the output of my logistic regression model. This is the output of my logistic regression model. Now we have to interpret the model by using the similar technique as we interpreted the linear regression model earlier. This is the output of the logistic regression, and this output is just similar to the output of the simple linear regression. Here we have estimates. The first estimate is the intercept, the second is the estimate beta 1. And we have here the p-values of the each estimate. Both of the estimates are significant because their p-values are very small. We can write down these estimates in the form of y as linear regression model. Minus 5.3, we can write down as 5.31 plus 0.111 age. I have rounded the value at the 3 digits. This is the y cap. If I plot the value of y cap, we have a linear function, but we have to transform it into the sigmoid function. So the sigmoid function can be transformed by very simple model, and that model is p cap is equal to 1 upon 1 plus e raised to the power minus y cap. This is your predicted probability. This is your predicted value of y. This is your predicted probability. So you have to convert in a simple way. So these the degree of accuracy of the model is null deviance, residual deviance, and the AIC. AIC stands for the Geiger information criteria. The smaller the value of AIC, indicating that the goodness of the model. The larger the value of the null deviance indicated the poorness of the model. Means the smaller values means the good model, the larger values. If I have the two models, suppose model 1 and model 2. The model 2 has a larger deviance than the model 1, so we can call it as model 1 is better than the model 2. If the model 2 has a smaller value of AIC than the model 1, so we call it as M2 is a better model as compared to the model 1, right? So this is the way to judge the model. Logistic function, there are the two forms of the logistic function. First form is this, and the simple form is this. What is this? This is your y cap. Nothing other than that. So you have just to raise the y cap in this form. E1 plus E minus y. Just remember the very simple function. Give us a predicted probability. Now we convert it into the odds. Before going to write down the model into the odd, we have to predict the age for, we have to predict the probability of having the CHD when age is 32. So just put 32 here. Your predicted value of the probability will be 0.147. Indicating that 14.7% chance that a person having the CHD when the age is 32. When age is increasing, the probability will also be increasing. Why? Because this is your age and this is your sigmoid function. As the age is increasing, the probability is also be increasing, and the maximum value of the probability is 1 at some level of age. Suppose it's the value of 90, at which we have a very high probability of CHD. So it's a very simple part to explain the model. Now we convert into the Logit function. Logit function is simple ln odd. ln odd. This is your odd. Probability of success divided by the probability of failure. It is equal to y cap. Very interesting part of Logit function is it is equal to the y cap. So what is the transformation? Just remove the ln from the left side. This will be in e raised to the power. Then p upon 1 minus p is equal to the e raised to the power. Then convert the each and every value. We will have the logistic function. So we can transform logit into logistic and vice versa. So this is your simple y cap. This is your simple y cap. If I put the age, any specific age, suppose 30, so 0.11 into 30 minus 5, this value will be equal to the ln p upon 1 minus p. But instead we are describing the betas here. This is what? This is beta naught, estimate of beta naught. This is what? This is your estimate of B1. So B1 is 0.11. In usual regression, if age is increased by 1 unit, we call as the y is increased by 0.11. Here we call it as the logit value, means ln p upon 1 minus p will increase by 0.11. If we increase the age by 1 unit, then the logit value will be increased by 0.11. This is the logit value. If the age is 0, then the logit value is minus 5.3. Right? So you can convert the logit values by taking their exponential. The value of B1 is E 0.11. If I take the E on the both sides, so this is equal to 1.12. The odd ratio. Odd ratio is what? P upon Q is the odd ratio, or ln P upon Q is the ln odd ratio. So what is the difference between P upon Q and ln P upon Q? P upon Q is the odd ratio and ln P upon Q is the ln of the odd ratio. And ln of the odd ratio is equal to this number, 0.11. So if I take the E, which is the anti-logarithm of the odd ratio, then I have the value of P upon Q, which is this one, 1.2. The odd ratio associated with the CHD in 1 unit change in age. If I change the age 1 unit, then the odd ratio will be changed by 1.12. So there are the several description of this. If age is increased by 1 unit, then logit value will be increased by 0.11. If age is increased by 1 unit, then odd ratio will be increased by 1.12. So there are the two versions of describing the slopes. Either the increasing in logit function or the increasing in odd ratio. Odd ratio is increased by 1.12 and the logit function will be increased by 0.11. So this is the conclusion of your model. Similarly, intercept. If I compute the e raised to the power b naught, which is e raised to the power minus 5.3, this is equal to 0.004. Means if age is 0, then the risk of having the CHD in the odd ratio is 0.0049. Very small value we have of the odd ratio for the age 0. Age 0 means the infant below a 1 year age, assumed as a age 0. Now the estimated probability and the log of odd when age is 15. This is the second part of the question. Firstly, I predicted the value as age is equal to 30. Now it is a problem for you to predict the probability log of odd whenever the age is 15. So nothing you have to do, just put the value 15 into all of the three equations. You will get the value of probability, you will get the value of logit, you will get the value of odd ratio. Three values you can determine. One is the value of probability. By putting 15, you can predict. So your answer may be in the form of probability. Your answer will be in the form of logit function, sorry.
ln P upon Q. Your answer will be in the form of odd P upon Q. So you have the three versions of explaining your output, either in the form of probability, either in the form of Logit, or in the form of log odd. नहीं, or in the form of log odd नहीं है वो, that is a odd ratio. This is odd ratio. This is odd ratio. This is Logit. And this is predicted probability. So in any of the form, you can write down the model. Now example 2. Example 1 has been finished. Now example 2 is started from this place. Acha, I am recording this example